So I'll start in a second. Okay. So, I got a bunch of stuff on the screen. Let me get all that off. Okay, so 2 or 3 things. One, I got a question sent to me the other day that they didn't see Wednesday's lecture or Friday's. One, Wednesday I forgot to turn on the stream. So I think I have the stream going. Has to be a little, so if y'all see me with a black circle and no red dot, let me know. So that'll tell me it. Friday I didn't do one, and I think I'll be here on Friday. And then I think after this next coming Friday, I'm going to say it's all virtual on Friday. Because I've seen 3 Fridays in a row where no one came, and I thought, well, I'll do a little bit and I'll leave. But I think instead of doing that, what I just did is I went through and so these are all chapter 1, and there's a little bit of chapter 2 in here. But then I started saying, okay, if you look at these, I have more hours of lecture than the 30 or the whatever it is. So there's plenty of stuff out here. So what I'll do is I'll say, okay, go look at this, and there'll be a problem or something like that in there. And this is under the video, and then you have that. I just put the titles on there. I'm probably going to put more titles back here so that you'll see those, and I may actually add some more to it as time goes by. But I'll fulfill or fill in all of that from here. So if you look at this, I don't know if you can, let's see if you can see. Like if I start that's 43 minutes. This is 9 minutes. That's an hour and 9 minutes. And that's 20 minutes. And these were made a while back, and I was trying to make these in such a way that they were not dependent upon the textbook I used. So you'll see it probably would be beneficial to go watch those. One of the things you can do is speed them up twice the speed, and that way you don't fall asleep or anything. So by all means, look at those. They're not perfect. I'm not trying to be perfect. I'm just trying to get some information in front of you. Around here, you don't have a lot of time to be perfect. So, but what I wanted to do today is I wanted to do this problem that's already done, but I wanted to lead you through it without looking at what he's done. And then we'll do another one that's in the problem set. So what he's got here is a tank. For whatever reason, it is what it is, and it basically has an angle here which I do not see the side view of this. Okay, so let me scroll down here for a second. Okay, determine the force the water pressure exerts on the inclined side of the plane of the storage tank. To me, he indicates kind of that the thing has these bolts. So I'm guessing he's trying to make sure these bolts don't pop off and the thing comes out. So let's just see if we can do this. First of all, he gives us 3, 5, and 6. So I'm going to redraw it sideways. And this is our 5. And the 3 is into the board. And you come over, and from here to there is 6. So give me a second. So really, the fact that you have something from here back to here doesn't really matter. So what I'm going to do is I'm just going to say, okay, I've got an object, which is 5, and the water level is like, assuming it's right to the top of this, so essentially here's your water. I'm going to draw it like water. There you go. Waves and stuff. And so, 2 things you can do. One, you can break this off, and I'll break it off over here. And, okay, so the force itself, the pressure down at the bottom should be 5. Is it water? I'm assuming it's water. Oh, water pressure. Okay, so it is water. So it is, okay, so gamma times H, which would be 62.4 pounds per cubic foot. And it is, you drop down 5 foot to get there. And so the pressure at the bottom, give me a second. Pressure, 5 times 62.4, 312. So the pressure at the bottom is 312 pounds per foot squared. Now, at the top, since the water touches the very top, it's pretty much nothing. So it's kind of like that now. That little part was an artifact that I should not have put on there. And so the water pressure is pushing up on this thing to try to push it, to try to break these little bolts or drill holes or something. So now the question is the location. He wants to know the value and the location. In this particular situation, you've got an area which is 6 by 3. So the area back here is 6 by 3 or 18. And the load itself at the very top, okay, so if you look at this from this standpoint, you say, I want to turn this into a statics problem. What you really want to do is take how many pounds per running foot. So if I take this and turn it all the way over like that, I will have something like this. So for example, this is point A and this is point B. Well, this is point A and this is point B. B being the location of the heavy, A the light. So I essentially took this thing, turned it all the way around like that. Now it looks like a statics problem. However, in statics, over here you wanted the pounds per running foot being running back and forth this way. So what do? You multiply it times 3. So essentially, this will be 3 times 312 or 936 pounds per running foot. So 3 times 2, 6, 3 times 1 is 3, 3 times 3 is 9. Now, you want to do this, you want to replace it with B, A, and a load that's sat right here. So you want to get the feed off there. So what you're doing now is like you did in statics, you find the area of the load diagram. So it is 6 long, and you want half of it because the upper part is gone. So you want 3 times that. Well, now I'm getting to the point where I've got to do 936 times 3, 2808, and it is located 1/3 from the heavy side. So it just turns out that that's 2. So that's the location. The heavy side, now you have to realize this was back over here. So this is essentially the A line, and this is essentially my B line up here. So B being, I'm sorry, I got those backwards. So B is the heavy, B is where the heaviest part of the load is, which is at the bottom. And A is where the no load is, which is at the top. So in fact, okay, he wants us to know that. Well, if this is 2, then that's 4. Now, let's do this the other way. This is what they call a pressure prism. The other way is you use 2 sets of equations. And this is the reason I picked this problem. F is equal to gamma H bar A, and I'll call it a little delta is equal to I bar XX over Y bar area. Now, let's look at the top one. The top one says the force is gamma 62.4, the location, the depth of the centroid, and the area of the whole plate. So let's see if this turns out to be 62.4, the H from, okay, so here is your centroid. This is C. It is 3 down, but it is also 2.5 here. So its depth is 2.5. Find the depth of the centroid, not this distance, but that distance. This would be classified as Y bar. This is classified as H bar. If you go vertically down, that's H. If you're going out the line of the gate, you're going out the Y. You'll notice you put it right here. So H bar is 2.5, and the area is of the whole thing is a 3/6. Yeah, 3/6. If you multiply all that out, and I guess I got enough patience. 2.5, 2808. Okay. Turns out that's the same thing you got over here. Now, this other term, okay, what is it? Okay, now first of all, Y bar and A bar, that's pretty simple. Y bar is 3 and A is 18. But what is that? That is, okay, you stand here, like inside the tank or wherever, or out here. Maybe you can stand out here. You look straight down at this thing. What do you see? You see a box that is 3 wide and 6 tall. You look, the bar says you look straight at the centroid. And then you tell me what I is at that point. I do 2 X's because legally they're supposed to be 2. It's a tensor. And it's 1/12 the base times the height to the third. What's the base? The base is 3. Height is 6 to the third. That's the term that ends up on top here. 3, 6 to the third over 12. Now, let's figure out what all this is. It's going to take me a minute. So, 6 times 6 times 6, wait a minute, 6 times 6 times 6 equals to, okay. And then divide by, oh, another 3, then divide by 18. It's 1. Now, think about this. What is that term on the drawing. That term is very specific. Here's the centroid. This is where the center of pressure is. Center of pressure is the location that if you broke this down to one load, that's where it's equivalently going about. The distance from the centroid down to that is what I like to call delta. And that's, in my mind, that's what I see. It's just, I have to remember that, and that's it. So it turns out that makes this equal 4, because that's 3, this is 1, that makes that still 2. So you matched and got the same answer that way than you got using the pressure prism. This works well if it's a flat plate like this. In other words, the depth doesn't change. And that's why I was going to do this one and then roll to the next page. And so let's see what he did on it. It looks funny and skewed here, but on the main thing, these are 90 degrees. They should always be 90 degrees. They kind of don't look like it, but you could imagine it's so close, but they're supposed to be 90 degrees. So of course he got his resultant force of his 2808, and of course he put down 4 and 6, and he's done. I do not know if he did this the other way. He did. Okay. So let's take a look at the term he likes and the term that I'm doing. Okay, so what he's doing, so if you look at this equation, and you got your gate here, and it was 3 down to here. In other words, this is 3. Then this is what he calls center C, and here's where the pressure, location of the pressure force is. So if I take this and move it to the other side and call it delta, that's what delta is. That's why I just have to remember that. If you want to remember the whole thing, that's great. I remember this, and I remember this is how far down past the centroid to the center of pressure. So of course, what does he have? 3 foot, and then plus is 1 foot. And that's pretty much it. So to me, I will always write them like that. And then remember that that's how far below the centroid that the center of pressure is located. Okay. So let's look at one. Okay, so let's say it like this. This, F, I erased it already, gamma H bar A, and my distance below the centroid to the center of pressure is I bar XX over Y bar area. Again, I'm not going to conform because I is actually a tensor. There are 2 components to it. In other words, Y and Y D area. That's what these are. Because if you want to do this, guess what you do? Now they recognize it's a tensor. And so that's just mundane and stupid to me. It's a tensor from day one. It's always been a tensor. Tensor means it has 2 components. You have already dealt with tensors. You may not. Here's your cube. You put a normal stress there, okay, and depending on your notation, it'll be the X direction and a face. And what do you do up here? Maybe this is, okay, so if that's X, let's say this is going to be Y, and let's say this is Z. So what is this now? Yeah, some books will list this as being tau, but if you get into continuum mechanics, they're basically the same thing. It's just anyway. So you'll be in a face direction. And then you'll have another one, a face direction. So this has 2 directions associated with it. So these are tensors. Guess what? So is this. Actually, there are components that you can get into the Z component. If you get into dynamics, in which you're taking bodies, they have an inertia about all three axes. It's an actual tensor. You can line it up and find principal axis of it, like the Mohr circle. So you can do that. So, in fact, let's go down and solve the next problem, which may be listed on a different page. I believe it is. It is different because it's only a circle. So if it is not a rectangle, good luck with that, because actually what you're supposed to do is you're supposed to integrate over the surface in which this force and this force is larger, but all along that line, that's all the same. And then you get a little longer, further down, it's all the same. And then what happens, you get down to this last little part and you get a little smart sliver in which it doesn't contribute as much. So you can't use the pressure prism very easily unless you're willing to look at the actual volume, which looks, I don't even know if I can do this, but it looks like an object which, if you extended this circle out in a drawing and sliced a plane through it, what you're going to see is out here, this big long oval, and the volume is associated with the internal part, in which part of it was a circle and part of it was an oval that you sliced through there. Good luck with that. I'm not doing that. I'm doing this. So what do I have to do? Well, right to the centroid. I know that's a circle thing. So I know the centroid is at the circle. So F is equal to gamma, which I guess this is water. Water, yeah. Oh, and it's meters too. So it's gamma, H bar A. Well, gamma for this is 9810 newtons per meter to the cubed. Why? Because density is equal to 1,000 kilograms per cubic meter. And if I want to multiply times G, that would give me this, or G would be 9.81. And then this is a definition. This is kind of how the SI system was set up. Part of it is that water maintains that 1,000 kilogram per meter cubed. So it turns out gamma is that. H bar, well, he just gave me that. That's 3 meters. And the area, pi, that's a diameter. So me looking for the shortcut, I'll take the radius over that any day and square it. And what I'll end up with is that. Let me see if I think I can do that math. 9810 times 3 times 3.14159 gets me about 9.2457 roughly newtons. And this is meters squared. So that's my newtons on that. It's 3 meters down, that's about 9 feet. And 1 meter across, that's about 3. So if I wanted to do a check, just give myself a rough check, I'd do 62.4, roughly 9 feet, but not exactly. And then pi times, well, if it's 1 meter across, that's about 3 feet squared. And this is not going to match out. About 15,878 pounds. Let me just do the conversion just to see how close I am, because 1,000 pounds to newtons. Well, 15,000 pounds, it says, is about 66,000 newtons. So I've probably, there's probably some levity of assumptions I've made there about some things. But we'll just go with this right now. Next thing is I need to know the delta. Okay, here's the centroid right here. So here's my C. Now somewhere a little below it, probably pretty close, is the P, the location where the equivalent pressure load goes right through there. So what I've got to do is I got to find I bar XX of a circle Y bar. What is Y bar? In this case, we're doing vertical. So, if you got the angle back here, well, okay, that's fine. This is H, and this is Y. But if it's vertical, guess what? H equals to Y. And so you can just as easily put 3 down here, and pi times a radius of 1 squared. Now I got to go find that. And so that's where, I know there's different places you can go search for that. I'm pretty sure there was oh, there it is. That's what I was about to say. Okay, so here I go, D. So it's pi, or say, okay, let me repeat myself. Pi r to the 4th over 4. Hey, that's convenient because I think r in our case was 1. That's really nice. So you notice it's the same because if you tilt your head, it looks the same. So end up with pi, and r in my case was 1, and so then I get a 4 underneath, and then a 3, and then another pi. So I get 1 over 12th, I think. Okay, I'm not betting anything on this, and so that's kind of what I see. Because I got a 4 times a 3, right? Because the length down to there was 3. Okay. Notice something else, and let me get to the picture, and I'll bring this up. Okay. So here's what's funny. Let's look at this term. Okay. I don't really care. Let's not worry about this, and let's not worry about that. But let's look at this for a minute. So here's what's so interesting. If I take this circle and I go deeper and deeper and deeper into the ocean, then that number becomes larger and larger and larger to the point where this number goes down lower and lower and lower. And eventually what happens is the center of pressure kind of goes closer and closer to the central. So if you get deeper and deeper, here's what you see. Do a side view of it. And so here's what you see. Here's the pressure really deep. And then here's the pressure really deep, but here's what's happening. It's only a small sliver. So you got the uniform part of the load, and then the little triangular part that comes because the height difference here. So pretty soon, this delta, if you go deeper and deeper, eventually coalesces with the central. And that's something to think about occasionally, but not, you don't really care that much about it right here. So let me get some of this off and let's see what he said. I would be surprised, shocked, and stupefied as if he didn't do, the way. Okay, so here he gets 3.8. Okay, I didn't finish it. Okay, so there's his delta. Okay, so I went 3 plus 1/12 is equal to, and that's what he's saying. Don't know. 1/12. Okay, is 3.083333 ... So that's what he's got here. This is what I'm finding. This is my delta. And like I said, the deeper you go, the deeper this is, this shortens and shortens to the point where it never really touches it, but pretty soon, if this is a window on a submarine that's facing vertical, you get a couple miles deep into the ocean, pretty soon that location of that load is pretty much right there at the centroid. Okay, so here he's got his 1,000. This is the row, times the G, times the H, times the area. And he did the 1 meter squared too, good for him. So I got the 92,456, he got 92,5. Using the table and inside back cover for circles, the resultant thing is that. So what I didn't look at the thing there, but that's what I got off of the Wikipedia, whatever. And there it is. Now I was lucky because my R was 1, so I never wrote R because the R was 1, so I just didn't write it. So technically, I should have done that, but I didn't write it. He did. I didn't. And I should have. So he wrote the 1 to the 4th. I should have wrote the 1 to the 4th. So we got the same two numbers. And now you have everything you need. You need the force and the location of the force. And that's pretty much it. So there are problems that have oddball shapes that you have to use this. I don't even know what the next picture looks like. It's probably a triangle because there you go. Okay, determine the magnitude, location of the reservoir acting on the triangular end plate of the settling tank. So in other words, he doesn't want it to break off down here. And so I guess we could do that real quick. It's a 2x4. It contains kerosene. I don't know so maybe we'll just look at that one real quick because I don't know the thing of kerosene. So here he just puts the resultant load, okay, the Y down to the P, but he didn't tell us the centroid, but the centroid, even though the triangle is listed this way, it should be 4/3. Did he put it anywhere? He didn't put it anywhere. It's okay. He should have. There it is right there. So we'll just look at this one real quick. It's the same procedure. Again, I'll take this one, which is that one, and then I'll look at this one, which is my delta, how far below the centroid. So he found the centroid is 4/3. And then he went in and found the IX of that triangle, put that up there. But before he did that, he went in and found the kerosene thing. I don't know what the kerosene is. Here's the distance, the H bar, and then the area is, it's a 2x4 triangle, looks like that, but you take half of it, you get 271 pounds. Then what you do is, of course, you found the centroid a minute ago, and that's all great. But then, he does this part up here. So he takes the IX, I bar XX, does the 2 and the 4, gets the number, and sticks it right here. Then he does the Y bar, and then the area, which is the same area as it is right there. And he gets that it's 2 feet, or this far below the centroid. So that's where he put his picture at. If you notice, it's 2 feet, right? For me, I would have gone in and I would have found this, and that would have been 1.333, and then I would have looked for the delta, which would have been I bar XX over Y bar area, and then I would have added those together or not added them together depending on what you need at that point. So your equations, those are the only two equations you need right there. That and that. Now, I got a few minutes, so I think I'll do a quick introduction to curve gates, although I don't think I can do any better than what I've done. Was that lightning?
Yeah.
Uh-oh. Let's see. Where am I at? It's got to be dark. Okay, that's a plane surface, geometrical method. Okay, so this is the, I think it's funny that different books call it different things. This is called a geometrical method. In other books, it's called the pressure prism. So it is a prism in which you take, believe it or not, if you wanted to do that, you could do this problem in a CAD thing. You could draw your surface, right? And then extrude it backwards. And then slice it with a plate. So that's all you're doing, slicing the plate, and then you're working on the prism. Essentially, you have an object, and maybe one day I should do a video on that. Odd-shaped object that is shorter on one end than the other. So it is this object, right? And you find the volume of the object and the centroid of the object. The volume would be related to the force. The centroid would be located, the location of the, C-A-T, location of that force. And maybe I'll do that one day. It's just, and maybe I'll do it this Friday as a replacement. So I might just, I don't know, I'll send you an email later. So we may or may not meet this Friday. If I do that, I might just pick a problem, and because sometimes it's beneficial to see how you do stuff. And if you have a CAD package, and most CAD packages have an extrude, don't they? I mean, I have a real cheap one. I'm not advocating this one or anything, but I had it for years, and I know how to use it. And so it's not the best one out there, but it's related to ages and ages and ages ago. But the thing for mine is, I paid now they're doing subscriptions. Oh yeah, that's great. Everybody's getting the subscriptions. But anyway, I paid $70 for mine way back, and I didn't have to do a subscription. So the thing I do there is you can make an object, extrude it, and then slice it. And maybe I'll do that and do a particular problem in the book doing that way. And that way it gives you an idea of what you're actually doing. So what you're doing is you're integrating over the surface, which, the resultant force is the volume of the pressure prism, and then the location is the centroid. And instead of doing all this math for a weird surface, you can just do it in a CAD package, and just push a button. What's the volume of that object, and where's the centroid? And those two objects, that's what you get. So maybe I'll do that. So be looking for an email. That'll give you some idea of a different way of doing it. I don't think you can extrude. There's this. Okay, so there's also FreeCAD. You can do, that's one thing. And then there's something called, let's see if I can find this one. Okay. This one's kind of nice because you don't pay anything for this. And it's an open source platform. It comes out of France. And if you look at it, it comes out of a company that's a multinational company that has 30,000 employees. So they've got a lot of, the thing really, that's the one I use right there. And so you don't have to, in other words, there's many different interfaces. You do not have to use the finite element associated with it. You can just use the CAD part. So maybe I'll do that. Maybe I'll make a little surface, extrude it backwards, and then slice it, and then look at the volume and then the centroid, and I'll pick a problem out of the book that's kind of bizarre, and maybe I'll use that one instead. Because think about it, you can just download this thing. It's free. So instead of using a CAD package that you have to go pay money for in a subscription, I'll use this one, and I'll show you how to do that. I'm all about using resources that I don't have to pay for. I have never paid for an app on my phone yet. I broke down and did an iCloud service the other day because it backs your phone up every night, and I've had an instance where I lost some pictures, and I decided, well, I don't need the stress of that. So if you go to this, you can go to download, and there is a Windows 10 version. It started as being only Linux, and then they decided that there was a lot of requests for a Windows version, but you'll see it's 1.6 gigabytes, and so it's a fairly large, it's a huge code, and it has a lot of functionalities with it, but I don't delve into all those. I delve into the parts that I deal with, and that's all. It'll do stuff. You can do a design, export it as STL, take it to a 3D printer, and wait a day or two, and your part comes out. Or you can send your part to if you want it made out of nylon, and you don't want to pay for a nylon. That's kind of the new thing. These 3D printers are all plastic parts, but if you hit it with a hammer a couple times, it just shatters. If you want something made out of nylon or metal or something like that, there's a number of companies that have all these 3D printers. You just send them a part, and then send them your credit card. A week later, you get your part made out of either metal or composite or nylon or something like that. And I just, I'm not going to pay $15,000 for a 3D printer to produce 4 parts, so I'm just not going to do that. So maybe I'll do that instead. So don't go buy that. Just go. I'll maybe just take you through. So this might be a multi-period thing. I might do an hour video. Open a Windows interface, say, okay, now you want to install this. Let's install it. We'll download it. I'll show you how to install it. I don't want to go through all of it. You can look back here. Not that I'm not trying, don't get me wrong, I'm not trying to toot my own horn or anything. Let's see. That's not, I don't, oh, there I am. So if you go back into videos, way back into the ancient times, okay, here you go. Here is a video that I did in 2015.
Let me show you.
Okay, that
where you go to get these things.
I'm running.
So if I just go to a browser.
Code that is inside of it's a Linux.
So it's the simplest.
This
is about the simplest thing I can think of.
Operating. So I'm drawing parts in there.
It's essentially a box. There are 6
taking you through
color
building the part, gridding it, and then eventually
static.
Getting to the point further and further,
the modulus
and
was
then
10 to the 12th or something like that.
Going through and doing a simulation. And then looking at, there's the object moving up and down. So it's like a weird looking beam. And so, I guess at this point, what I was trying to say is you get a fat, thin. Okay, so beam theory works great until you have a fat, tall beam. And then the beam equations don't work because you're mostly in shear, but you'll still get a deflection. And so if you go in here and you do it, a simulation in this thing, you can see it. You can see the thing. And you can get the answer. But if you make the beam thinner and you try to match the beam equations, it matches perfectly.
Okay. Will that support SolidWorks files?
Yeah.
Common.
Yeah. You gotta, Okay, so there's two things you can do. There's, what's it called, ASIC, and another one. There's two standards. I can't think of the other standard, but you can dump it in SolidWorks. You can dump files out of this into that, whatever that other thing is, go to SolidWorks, and it loads it right in. So you can interchange between the two.
Because we don't have it to where you can do the stress analysis on it for the one we have at work.
Oh.
Using a free one would be.
Oh, okay. This will do both. See, the thing is, if you got SolidWorks, I would stick to the SolidWorks and dump the file and load it in over in this one, and then do the stress in that. Because otherwise, okay. Now I'm speaking from inexperience because I've spent a small amount of time on SolidWorks, and then I spent a large amount of time here because I'm not willing to pay. So I kind of feel, this is just my gut reaction, is that I can learn on this Salome CAD and figure out everything, and if it changes versions, it doesn't change that much. And so I've learned how to do that. Now to me, I'm not going to go back and learn SolidWorks in order to do that, but if you've got the experience doing SolidWorks, and everybody does, just dump all your files, pull them over and pull them all in, and they'll all be there. So I'm not advocating abandoning them, but there are three major 3D driven codes out there: parametrics, ASICs, and this thing called Open Cascade. Open Cascade is the European thing in which Salome and FreeCAD are based upon. But if you look at the main libraries between those three, they're almost the same thing. And so three companies, one's out of Denver, one's out of Boston, and this one's out of Paris, I think. And so if you look at Salome, I think the company is a nuclear company that owns them, EDF or something. Okay. And it's a big company. Let's see. Who owns them? So they basically, you have to look around down in here. History of Salome, maybe that's. Okay, so Open Cascade. So it's based on Open Cascade, which you can actually go get that library. But it is, I've downloaded it. It is unbelievably massive. But it's like what's it called? Paraworks, right? Out of Denver or something. But it has all the libraries. If you want to get deep into this, but if you just want to use the CAD, okay. What EDF? Okay. EDF. Okay, I may have this EDF. I think it's that, but I'm not sure. Yeah, it's that company. About us. Okay, this is big. Biggest generator of zero carbon emissions, but they're in nuclear renewables. I mean, it's a big energy company. It's European, so it's pretty large. Okay, what in the heck? I don't know what all that is, but I think one time I saw it was like 30,000 total employees nationwide or worldwide. Let's see if I can find. I mean. I may be able to find it on Wikipedia. Usually you can. Oh, okay, here we go. It's out of Paris, founded in 46. Okay, 165,000 employees. Revenue is $84 billion. So the thing is inside this company is where they developed this. It meets the European nuclear regulatory body, so but it is an all-encompassing huge code. I mean, it has everything from contacts, and that's hard to find. In other words, if you had an object that was, say, piece of metal and it came down on the body and started pushing and sliding it across. You have a friction, but you also have force that's transferred through that. That's not a connection. That's a different way of modeling. And most finite element codes struggle to do that. But this one has a way, it has 4 or 5 different ways of interfacing two objects. So if you had friction occurring inside of a motor or something like that, it could take that and you'd have to model it. What it does is it does a face, and then off of all these faces, it'll come up with a friction coefficient across each one and do it. But it is not for the faint of heart. I mean, if you're going to do contacts, you're probably going to have to go to a training, but you'll find you may end up having to go to Paris or something to do a training on it. But it's pretty impressive what it's capable of doing. So I just don't feel like, I mean, I'm off over doing this, and I was doing that at one time in my life, and I've abandoned all that, and now I'm over here. So I still know how to do some of this. But if someone said, well, can you solve this problem for me with friction and stuff? Well, I could, but I'm not going to, because I don't want to. I'm over here, you know, and I've had that before. So, but, you know, because the thing is you could, it may take you 2 months of your life to do it, and it's like, no, I'm done, you know. So I'll use that. What I'll do is I'll start it up. I'll show you how to download it. I'll do the whole thing.